In this video, we just want to look at using maybe vectors in our work energy problems. And just a quick wee summary just of some of the things we've seen so far. We've used our UVATS equations. We've used our Newton's second law. We know what potential energy, kinetic energy is. We've seen work done as force times distance, or Fs, force times displacement. And most of these are fairly straightforward when we use vectors as well. We can use our components, our I, J's and K's. But some we need to be a little bit careful about because something like V squared and U squared, 2AS, those are two vectors being multiplied together. And we need to be careful when we do that. Force times displacement, need to be careful when we have two vectors multiplied together. And the way that we're going to do that is by using our dot product, which we've learned in pure maths. And so, for example, if we wanted to do the dot product of A and B, where A was 2i plus 3j plus 4k, and B was I minus 3j plus 5k, then to dot them together, we write them beside one another. We take the magnitude of the I components, multiply them. So 2 times 1 is 2. We multiply the magnitude of the j components. 3 times minus 3 is minus 9. And the same for k components. 4 times 5 is 20. And then we find out what that is, and it gets us a number. It's a scalar dot product. It will always come up with a number for that answer. And so we can take that into some questions on work energy and work energy equivalence. So here we've got one here. Particle P is acted on by a total force, F, where F is written in terms of I's, J's and K's. So I guess we should underscore all of these. Calculate the work done by F as P moves from the point A with this position vector relative to the origin to the point B with a second position vector. Oops, so it should be under the J. Well, we know then that work done is F times S, force times distance or displacement in this case. So we know what the force is. We've got that. So I'm going to write it. And I'm going to write it in column vector form. I'm going to write it as 5 minus 2, 3. But we need to work out what this displacement was. And it's going from point A to point B. So we need to find the vector AB. Well, that's going from A to O and then going from O to B. And going from A to O is the reverse of OA. So that's minus this position vector of A, and OB is the position vector of B. So in this case, let's keep going with it. That's minus 6, 5, 1 plus, and we've got 8 minus 7, 6. And that equals then 2i minus 12j and 5k. So this is our displacement. This is the vector AB, 2 minus 12, 5. So I'm going to put that in here, 2 minus 12, 5. And then we just use our dot product in this. So the I components, 5 times 2 is 10. Minus 2 times minus 12 is plus 24. And 3 times 5 is 15. And so our total work done here is 49, and in units, and we've got 49 joules. A second example, something similar. A small smooth ring of mass 0.5 kilograms moved along a smooth straight wire. The wire is smooth. The only forces acting on the ring are a constant force F and the normal contact force due to the wire. The ring is initially at rest at point P with that position vector. Find the speed of the ring in meters per second as it passes through the point Q with a different position vector. Okay, so we're going to go something similar here. I want to find out first of all, what is PQ? How do we get from P to Q? And I know that that's going from P to O first, and then O to Q. So P to O, well, the position vector of P is 1 1, 1. So if I do that the other way, it's minus 1, 1, 1. And the position vector of Q is 3, 2, minus 1. And so I put those together. 3 minus 1 is 2. 2 minus 1 is 1. Minus 1 minus 1, minus 2. And so there's our vector PQ. Now, again, the work done here is going to be the force times displacement, which is 5, 2, minus 3. I'm going to dot that then with our 2, 1, minus 2. Now it does mention there's another force, contact force, normal contact due to the wire. But if you think about it, the force will be acting along the wire, and that force will be at right angles to this normal force and to the displacement. The displacement then, when you dot it with your force, will be 0. So there's no work done due to this normal contact here. But when we put this in, then that's 5 times 2 is 10, 2 times 1 is 2, and 6, so that's 18 joules. Now, we're told here that the ring is initially at rest, and the work done here is going to be the increase in kinetic energy. So 18 joules is going to equal, well, it starts at 0, so we're just finding its final potential energy here. So it's a half times the mass times v squared. And like I said, when you take the other half times the mass times its starting speed, which is 0 squared. So that just is cancelled out. Excuse me. So 72 then equals v squared, and v is equal to the square root of 72, which is 6 root 2 meters per second.